By default, computer networks are built for one thing: pure, unadulterated speed. They are designed to move data from point A to point B as fast as physically possible, without asking any questions. That frictionless efficiency is highly effective for loading a web page, but it's completely blind. The network will route a malicious malware payload just as quickly and happily as a harmless email. This creates a massive engineering problem. Network administrators have to filter out those active threats in a fraction of a millisecond, but they can't afford to slow down the entire system by opening up and reading the contents of every single piece of data that arrives. The solution is a mechanism called an access control list, or ACL. You can think of it as a router's digital bouncer, a strict, unbending set of rules that decides exactly what gets in and what gets dropped. Because raw speed without security is a massive liability, these lists serve as the mandatory first line of defense for almost every modern network on the planet. When outside traffic physically arrives at a router, it usually enters through an ingress interface, like one of these gigabit Ethernet ports. This is where it hits that first checkpoint. Instead of bogging down the CPU by reading the heavy data payload inside, the router performs deep packet inspection. It strips away the outer layer and strictly examines the packet's exterior header. The ACL is looking for three highly specific pieces of information: the source IP, telling it where the packet came from, the destination IP, showing where it wants to go, and the protocol port number, which identifies the type of application it's trying to use. To process this, the router uses top-down sequential logic. It takes those three data points and compares them directly against its programmed list, starting strictly at line number 1. If the packet's header doesn't perfectly match the criteria on that first line, the router instantly rejects the rule and moves down to evaluate the second. It continues scanning until it hits the first match wins rule. The exact millisecond a packet matches a rule's criteria, the router immediately executes the action assigned to that line, whether that's permitting the packet to pass or denying it entirely. Crucially, once that first match is found, the router puts the list away. It completely aborts reading any of the remaining code. This strict abortive logic is what allows network hardware to evaluate millions of individual packets every single second without crashing under the computational weight. But this raises an important security question. If a clever piece of malware manages to bypass all the explicitly written deny rules on the list, but it doesn't match any permit rules either, what happens to it? It hits the implicit deny. At the very bottom of every access control list is an invisible, unwritten final rule that catches all unknowns. If a packet reaches the bottom of the list without a match, it is immediately dropped. This means that unless a specific type of traffic has been explicitly invited in by the network administrator, the router's automatic response is complete destruction. Operating from a default stance of no is a core philosophy in cybersecurity. It guarantees that even if a brand new, entirely undefined threat arrives at the gates, the network remains secure. Zooming out from the logic of a single packet, we find that writing a good rule is only half the battle. An access control list's effectiveness depends entirely on where you physically place it on the network map. There are two main tools at an administrator's disposal. The first is a standard ACL. This is a fairly broad, blunt instrument because it filters traffic based on only one metric, the source IP address. Because it's so heavy-handed, network architects have a strict rule. Standard ACLs must be placed as close to the final destination as possible. If you put one at the entrance, you risk accidentally blocking a user from accessing the rest of the network entirely. The second tool is the extended ACL. This acts as a highly precise surgical checkpoint, filtering packets by source, destination, and port number. Because extended ACLs are so specific, administrators clamp them onto routers as close to the source as possible. This destroys bad traffic the moment it enters, before wasting valuable internal bandwidth. These lists are rigid, uncompromising, and completely lacking in intuition. Yet, by combining unyielding mathematical logic with strategic physical placement, they form the absolute bedrock of global internet security.